Hello and welcome to another video in our Fundamentals of Geometry series. In the last video, we had talked about cyclic quadrilaterals. In this video, we'll be talking about a theorem which is very pertinent to cyclic quadrilaterals itself, and it's called the Ptolemy's theorem. So let's get into the topic straight away and let's understand what this theorem states by directly looking at its derivation. So what I'm going to do to derive the Ptolemy's theorem is that I'm going to be considering, let's say, a straight line drawn from B onto AC, such that this straight line is being drawn such that angle, let me call this line, say, BK, such that angle ABK is equal to angle KBC. Let me write this down here so that there's no confusion. Angle ABK is equal to angle, rather not KBC, is equal to angle DBC. So definitely, if I consider this angle ABC of the cyclic quadrilateral ABCD, then one of the angles ABD will be greater or lesser than the other angle DBC. So in this case, I'm considering that, let's say, angle DBC is greater than angle ABD. So in that case, I'm drawing BK in such a way that angle ABK is equal to angle DBC. Now, when this happens, and because of these two angles being equal, I can say that the triangle ABK is similar to another triangle in this figure. So which triangle is it similar to? So to understand that, let's look at this angle of triangle ABK. If we consider triangle ABK and if we look at angle BAK, then this angle BAK is nothing but angle BAC as well. Angle BAC is an angle subtended by the chord BC in the major segment of the circle. So another angle which is also subtended by the chord BC on the major segment is angle BDC. So this angle will also be equal to angle BAC. So angle BAC and angle BDC are equal because of a theorem in circles that angles subtended at the same arc by the same chord is equal. So that means that I can say that triangle ABK is similar to triangle BDC. Right? Why? Because angle A and angle D are equal. And similarly, angle B of triangle ABK is equal to angle B of triangle DBC. So two angles are equal. That makes triangle ABK and triangle DBC similar to each other. Now by applying the ratio of corresponding sides are equal between these two similar triangles, I can get a pair of ratio of corresponding sides as AK by DC is equal to AB by DB. Right? AK by DC is equal to AB by DB. Now similarly, just like how angle ABK and angle DBC are equal, that's how I made the construction. This automatically means that if I subtract on both sides of this equation, where angle ABK and angle DBC are equal, if I subtract on both sides by angle DBK, then this should also be equal. So angle ABK minus angle DBK is equal to angle DBC minus angle DBK. And angle ABK minus angle DBK will be equal to angle ABD. And angle DBC minus angle DBK will be equal to angle KBC. So which means that this angle, let me denote it by this symbol, will be equal to this angle. Because I'm subtracting angle DBK, the same angle, from two equal angles. Now, when this happens, I can now look at triangle KBC and maybe I can determine another triangle which is similar to triangle KBC. So which triangle is similar to triangle KBC? For that, I can consider this angle. Look at this angle, angle BCK, which is an angle of triangle KBC. And angle BCK can also be referred to as angle BCA. Angle BCA is an angle subtended by the chord AB on the major arc of the circle. Another angle subtended by the chord AB on the major arc is angle BDA. The BDA and BCA both are being subtended by the same chord and the same arc. So these two angles will be equal. That means that I can say triangle KBC is similar to triangle ABD. Because in triangle ABD, I've got two angles. Angle ABD is equal to angle KBC. So angle B for both the triangles is equal. And angle C of triangle KBC is equal to angle D of triangle ABD. So I can say that triangle KBC is similar to triangle ABD. Now, because these two triangles are similar, again, one pair of ratio of corresponding sides between these two triangles is, I can say, KC by AD is equal to BC by BD. Now what I'm going to do is, I'm going to do a very simple thing. In the first equation here, I'm going to cross multiply BD to the other side. So I get AK into BD. And cross multiplying CD to the other side, I get AB into CD. Similarly, here cross multiplying, I'll get CK into BD will be equal to BC into AD. Now, if I add these equations, this equation and this equation, if I add them, and adding them on the left-hand side, I can take BD common. And inside, I'll have AK plus CK will be equal to AB into CD plus BC into AD. Now, AK plus CK is nothing but AC. So I can say BD into AC will be equal to AB into CD plus BC into AD. This is what the Ptolemy's theorem states. That for all cyclic quadrilaterals, product of the diagonals will be equal to the sum of the products of the opposite sides. Not a theorem which is generally required to solve questions in most aptitude-based examinations. It's a slightly advanced level theorem, but it's still a very classical geometry theorem, which is true for all cyclic quadrilaterals. The product of the diagonals of a cyclic quadrilateral will be equal to the product of the sum of the products of the opposite sides of the cyclic quadrilateral. In fact, I'll give you a small work to do. As a homework, what you can do is, if you can see that when you try to apply this particular theorem to a rectangle, by the way, I've discussed before in the cyclic quadrilaterals video itself that all rectangles are cyclic quadrilaterals. So if you apply the Ptolemy's theorem on rectangles, you'll find that it gives you one of the most famous theorems in geometry. So figure out, try to apply this to a rectangle and then see that which theorem does it produce as a result of the application of the Ptolemy's theorem. Thank you.